Welcome to today's CNS Micro CT introduction. We acquired a system from Zeiss with model number Versa 620 in August 2019. The system has 4 separate workstations, one for controlling the instrument, 2 for data analysis, and 1 for diffraction contrast tomography. The system is a non-destructive 3-dimensional imaging technique which length scale from a few hundreds of nanometers to a few tens of millimeters. All instrumental components are housed inside an environmental monitoring chamber. The left side is our transmission X-ray source with tungsten target, and the right side is our X-ray detector unit. The center part is our sample stage, which can move in all 3 directions and rotation. On the X-ray source unit, the system has a pre-installed X-ray filter wheel. And the tiny hole in the center is our X-ray aperture, which provides a cone beam X-ray. For a detector unit, we still have a flat panel detector for imaging large sample. And we also have a series of objectives which can perform second stage optical magnification and give us some micron resolution. Now let's take a look at a micro CT dataset for a 3D printed microfluidic device. The overall sample size is about 1.9mm by 4mm with channel size at around 50 micrometers. X-ray will be exclusively absorbed by electron in our material and generate a grayscale projection image. Hence, we will first take a series of projection images, also known as a 2D radiograph, around the entire sample. Next, we will perform reconstruction and segmentation on the dataset so we can visualize it and perform 3D volume rendering. For this dataset, I try to segment out the fluidity channel as a pink color on the screen, so we can inspect the printing quality on the channel wall and observe any potential crack and defect inside the channel. Now let's take a look at the first special application. The system has a separate in-situ deep-bend stage which can perform both mechanical testing and temperature control. The deep-bend stage has a carbon glass chamber about 60mm in diameter. The mechanical force can be applied up to 5000 Newton and the temperature setting can vary from -20 to 160 Celsius degrees C. Now let's look at an in-situ tensile testing experiment we have done with Vanessa Sanchez from Harvard Engineering School. Vanessa is currently researching on different textiles for soft robotics and autonomous garments. The material we test in the system is some nylon jersey knit she fabricates. We first load her sample on the stage and perform micro CT scanning before and after the in-situ tensile testing. The video on the screen is a live image after extending her sample for about 3.532mm. Next, let's look at another special application. We can perform propagation-based phase contrast imaging. When X-ray transmits through a material, both its amplitude and phase have been changed. By capturing the phase change, we can enhance the contrast, especially for low-Z material and biological soft tissue. What we will do is proportionally increase the distance between the X-ray source to the sample and also the distance between the detector to the sample. The sample you are seeing on the screen is a piece of wooden plant from Davis lab from Harvard Herbarium. For phase contrast imaging, we will change the distance between X-ray source to sample from 25 to 50mm. Next, we will also increase the distance from the detector to the sample from 7.5 to 15mm. Now with longer distance, we can capture the phase shift and enhance the contrast. Now let's look at one example of using phase contrast imaging. The sample is a human cochlear bone from Xiaojian in scientific group at Max Ear and Eye Infirmary. The image are reconstruct 2D slice image. It's always very easy to observe bone structure as shown in the white region here. However, it's pretty challenging to get any clear soft tissue information inside the bone without any staining. Here is two comparison images from one of the soft tissue region inside the cochlear bone. The right side image shows we can capture much more detail with face. Now let's discuss the final spatial application, the diffraction contrast tomography. This technique allows us to generate crystallographic information in 3-dimensional. For diffraction contrast imaging, we will first need to implement two additional components, an aperture and a beam stop. With both aperture and beam stop along the X-ray beam path, we can capture the diffraction information for the sample as the cartoon is illustrating on the screen. Now let's look at one example. The sample is a piece of aluminum copper alloy from X-Nova technology. The sample is a cylinder with a 3.4 mm in height and 1.4 mm in diameter. We first take a standard absorption micro-CT image. Next, we will take a diffraction image with both aperture and beam stop in place. After reconstruction and segmentation of a small portion of the dataset, we can start to work on each grain boundary. We can label each region by its grain ID and observe the information not just in 2D but in an entire 3D volume. We can also color coding each grain by the inverse pole figure mapping. The picture is labeled based on the aluminum grain orientation in the Z direction. Finally, we can also label each grain by its size and perform some statistical analysis.